Dr. Peter Eisenhart.
Thanks, Amy. So as we've been saying, WISE is going to observe everything in the universe that's further away from the sun than the Earth is. And Amy's just told you about the objects that come closest to the Earth, the near-Earth asteroids. I'm going to move on out beyond our solar system and tell you about some of the superlative objects that we'll find in the rest of the universe, the closest stars and the most luminous galaxies. So in the next graphic, we see a representation of several stars, beginning with our sun in the upper left corner. And then as we move to lower mass stars, stars become cooler, and therefore they put out more of their light in the infrared wavelengths that WISE is sensitive to. If we go to lower masses still, we get to what's called a brown dwarf or failed star. These are objects that have less than about 8% of the mass of the sun, or equivalently about 80 times the mass of Jupiter. And you can see Jupiter there for scale. It's only a little bit smaller, but much less massive. So these are brown dwarfs or failed stars are putting out essentially all of their light in the infrared, and they're optically invisible. So WISE is going to find lots and lots of brown dwarfs. So if we look at the solar neighborhood as shown in the next graphic, this is a simulation of the neighborhood of the sun using the star systems that we know about now, going out to a distance of 25 light years from the sun. And there are about 100 star systems in this volume of space. You can see that some of those stars are much brighter than the sun, but a lot of them are fainter. Now what's interesting is that from previous studies, astronomers know that there should be roughly as many failed stars or brown dwarfs that can't sustain the fusion reaction, which is what keeps the sun warm, as the fusing stars that we see here, the ones that stay hot and glow invisible light. So of these 100 nearest stars, only a handful of those are actually brown dwarfs. And so there should be lots and lots of more brown dwarfs in there, but we just don't know where they are. Well, WISE is going to survey the whole sky and find these nearest neighbors, as shown in the next graphic, and that's going to transform our view of the solar neighborhood. And it's possible that one of these nearby brown dwarfs is even closer to the sun than any star that we now know of. The closest star that we know of now is called Proxima Centauri. It's about 4 light years away. Brown dwarfs have evidence for planets around them, and so we might also be finding the nearest planetary systems. That's evidence that would come from follow-up observations with more powerful pointer telescopes, such as the James Webb that John mentioned. Okay, I'm now going to leap beyond our solar neighborhood. I'm going to talk about objects that are not hundreds of light years away, not thousands of light years away, but millions and billions of light years away. We're going to leave our galaxy behind and go to a nearby galaxy shown in the next graphic. And this one is called the Cigar Galaxy, also known by astronomers as Messier M82. On the left, you can see a picture of the Cigar Galaxy in visible light. You can see that it's relatively normal looking. It's got a little bit of disturbance, a dust band running across it. But when we go to the infrared view that's shown on the right, which is from data from the Spitzer infrared telescope, you can see that something truly dramatic is going on here. And what's going on, in fact, is that M82, the Cigar Galaxy, is a starburst galaxy. It's forming stars at a very high rate, 10 times higher than our entire Milky Way galaxy, even though this is actually a smaller galaxy than the Milky Way. Our predecessor survey, the Infrared Astronomical Satellite, discovered there's a class of objects called ultraluminous infrared galaxies that shine with over 1 trillion times the light of the sun, and most of that light comes out in the infrared. And these are super starburst galaxies that are forming stars at a rate that's even dozens of times higher than the Cigar Galaxy, maybe even hundreds of times higher. So these are really cataclysmic galaxies in formation. They're rare today, but from studies with Spitzer, we actually know that they were much more common 10 billion years ago when the universe was 3 or 4 times younger than it is today. Now, WISE has been designed so that it can detect these cataclysmic, dusty forming galaxies out to a distance of 10 billion light years over the entire sky. So we're going to find the most super duper, hyper, ultra luminous forming galaxies in the universe, and we'll see just how extreme this forming galaxy process can get. And these are also going to be the most rewarding objects for follow-up studies with more powerful pointer telescopes, such as upcoming Sophia Herschel, which is in orbit, and the upcoming James Webb. So to sort of wrap things up here, WISE is going to carry out a sensitive infrared map of the entire sky, and it will allow us to learn lots of things about the objects that we already know about and find even more superlative examples, the closest stars, which I've described, and the most luminous galaxies. But perhaps the greatest benefit of an all-sky survey is that you can keep coming back to it. There are objects that are likely to be discovered years after the WISE survey is complete. And if you want to know the infrared properties of those objects, you can come back to the WISE survey, and the catalog and Atlas will tell you all about it. There are papers, hundreds of papers being published today by astronomers based on the infrared astronomical satellite survey 25 years ago. Still, every year we get hundreds of new papers that refer to that survey. So that's why we like to say that the legacy of all-sky surveys endures for decades. Thanks.
Thanks, Peter. And you've heard from our panelists. Now we'll open to the question and answer portion of our briefing. We could have the media start by identifying yourself, your media affiliation, and if possible, please target your question to a specific panelist, if at all possible, to eliminate any confusion. And for those on the phone bridge, if you have a question, push the *1 keys on your telephone to let the operator know that you have a question. With that, do we have any questions here in the audience? Okay, we have somebody online from JPL. Go on, you're on.
Hi, this is Emma Gallegos from the Pasadena Star News, and I just wanted to know more about what the budget is for WISE.
I'll take that. The budget for the entire WISE project is about $320 million. That includes the development of the satellite, the development of the mission operations, the execution of the mission operations, and the launch vehicle.
All right, thank you. Our next person on the phone is Ann Ryman from the Arizona Republic.
Hi, thank you. I was wondering if you could talk a little bit about how big this satellite is in terms that people could understand if it's, I don't know, the size of a car or a bus, and then how far up in our orbit will it be? Like how many miles up will it be?
I'll take that one too. Our media guide says it's about the size of a polar bear. Now, most of us don't run into polar bears, fortunately. The analogy I like is it's about the size of a race car, and it's more sort of, I compare it to a race car. It's a very highly efficient machine, custom machine, about 1,400 pounds, so it's a small car. That would also be a reasonable analogy for people's daily experience. As far as the orbit, it's 325 miles above the surface of the Earth, circular. And it runs along the day-night terminator, so it's sort of looking at sunset, sunrise continuously.
All right, do we have any other questions here in the audience? Okay, well, then we're going to go ahead and conclude today's media conference. I'd like to thank the panelists first off before we close. Appreciate your time. And if you'd like more information about WISE, by all means, join us on the web at www.nasa.gov/WISE. Thanks for joining us today, and have a great day.